Okay, so let's get started again. So, hopefully you guys enjoyed the first two lectures. I know I did. I think one thing that was underlying both of those lectures was this concern of choosing wavelengths or even the nature of your source, i.e. whether it's a focus beam or a broad beam, and being sure you're able to get the light to the right place. And so the key thing here, obviously, is that the nature of the light field that you're going to generate in the tissue is dependent on the nature of your source, the optical properties of the underlying tissue, and of course the wavelength of your source. Okay, and so all of these impact where the light goes. And so it's really essential that in order to design therapies, that we have an understanding of how these optical properties, the wavelengths, and the nature of the beams generate an internal light field. And then the other thing that we will be concerned about and is that, of course, this internal light field is communicated at the surface of the tissue, and that's this interaction between what happens below the surface of the tissue and its communication with the surface, which enables the whole field of diagnostics. Okay, and so, and that's what we're going to see in the days ahead. But today, I'm going to focus mostly on these internal light fields that are generated by collimated beams, and hopefully we'll gain some insight as to what are some reasonable ways to model these situations, and the strengths and weaknesses of these various approaches, and then gain some intuition as to how, when you adjust the nature of the beams, you adjust the optical properties, how that ultimately affects the internal light field. Following this talk, we're going to have lunch, and then the director of the laser clinic at the Laser Institute, Dr. Stuart Nelson, who I think Dr. Kelly referred to, will give us a tour of the clinic. And then you'll have many graphical user interface exercises where you're going to get to play with both analytic diffusion-based solvers as well as Monte Carlo solvers to visualize light fields. And also you'll do a little bit with reflectance as well. Okay? Before I move forward, any questions? Okay. Again, I want to keep this, like the first day as interactive as possible. Just at any point, don't hesitate to ask questions, and I'll try and be sure to pause at various points in time. Okay. Why is this not advancing? There we go. Okay, so here's the overall lecture outline. So on Monday, both myself and Jerry gave presentations where we talked a bit about radiative transport equation and the diffusion approximations, which is an analytic means to simplify the radiative transport equation that allows us to generate solutions. I'm going to talk about where standard diffusion comes from, and I'm also going to talk about a variant to the standard diffusion or P1 approximation. It's called the delta P1 approximation. And the reason I want to talk about this is that if we consider the history of radiative transfer, I don't know how many people know this, but radiative transport really started first, I think, in the field of astrophysics, and then later on neutron transport nuclear reactor theory. And if you just recognize that in those fields, they don't really run into collimated beams, right? There are no natural interstellar sources that emit light in a collimated beam. There are no nuclear sources that I'm aware of that generate collimated beams. So the shortcomings of classical radiative transfer to handle highly collimated beams really, I think, was fully exposed in the field of biomedical optics. And there are some analytic means to improve these classical approximations. And the delta P1 approximation is one that is actually relatively simple and provides significant gains in the accuracy of these analytic approximations compared to the standard diffusion approximation. So these, so we'll look at these two. And it turns out that this is really only a very minor variant off of standard diffusion, yet gives you great benefits. Then, as we all know, that once you have a governing equation, you haven't quite finished defining your problem in a mathematical sense, right? You need boundary conditions to solve your problem. And so we'll talk about boundary conditions, and of course, usually we're interrogating tissue at a tissue error interface, so we have to deal with the refractive index mismatch. We'll talk about how we deal with that, both in terms of stochastic solvers, which we've heard about from Jerry yesterday, as well as these analytic solvers. So we'll talk about how this refractive index mismatch, what we know about what happens at these boundaries, communicate as far as boundary conditions. And of course, we have sources, and we have to figure out how to represent those sources within an analytic context. I then want to talk a little bit about optical depths. Right? We heard Dr. Kelly talking about tuning wavelength, whether you want to get at vessels at this dermal-epidermal junction, whether you need to get below, past the vessels to hit the melanocytes, or if you want to get even deeper to get into tissue water in the dermis. And so what's really important is where your light goes. And there are various ways you can actually come up with metrics to characterize how deep your light goes. And so I'm going to introduce two different metrics, and one is going to be called the optical penetration depth, which is the depth that your fluence rate drops to a certain value compared to your incident light. And then an optical dose depth, which means that, okay, if this light is going to be absorbed, because it's usually the absorbed light that generates a therapeutic effect, where is most of your light actually deposited? And that's actually a little bit more superficial. And so that also, by defining those two depths, we can actually more quickly understand where these analytic models do a good job and where they do a bad job relative to Monte Carlo simulations. Okay, so we're going to use that. And then I'm going to look at, try to develop some intuition here. Number one, how does refractive index mismatch impact your internal fluence distributions as well as optical properties? Look at beam diameters. I think, Joseph, you asked a question, why can't you focus? Okay, and there are advantages to focusing and disadvantages to focusing with it because you have this highly scattering context. If you remember Professor Padma's lecture yesterday, they do highly focused light, and they really can't get images beyond 200 microns. And part of it is because the focus beam falls apart because of multiple scattering. And therefore, you can't generate those high intensities necessary to generate that nonlinear optical effect. So we're going to talk about that. And then I'm going to talk a little bit about how these fluence distributions then communicate to reflectance, maybe show a few reflectance results if I have time. If not, we'll just end with a summary and we'll get to reflectance in the coming days. Okay? Okay. Great. So, remind you about radiative transport equation. Hopefully we don't have to spend too much time on this unless there are questions. Remember, all radiative transport equation is that it's a balance equation. The key thing that we need to recall here is that the key dependent variable is the radiance, and the radiance is a function of both location and direction. And also time, if you have a time-varying source. But if you have a steady state situation, which is what we're going to be concerned about today, tomorrow we'll look at time-varying sources. You just have to worry about position and direction. Okay. Any questions on this since we've spent a couple of days since? Okay. So the question is that, well, this is difficult to solve. Analytically, there have been solutions to this equation done analytically, but they are computationally intensive and they're not necessarily easy to understand. But you can certainly solve this exactly using stochastic methods, as Professor Spanier talked about yesterday. But certainly in the early days of this field, in late 80s, 90s, Monte Carlo simulations were certainly very slow because of computational power, and people were eagerly interested in developing analytic solutions analytic approximations. And so, hence, gave rise to the diffusion approximation. So, the nice thing is that many applications in our field tend to operate in this diagnostic or therapeutic window between around 600 and 1100 nanometers, where we know that we have deep penetration in tissues because the absorption drops, but we still have high scattering. Okay, so because you have high scattering, once the light has undergone a lot of scattering, it has lost memory about its initial direction. And therefore, if you look deep in the tissue, the photons are pretty much traveling in all directions. Okay? So what people did is that, well, they say, okay, we need to somehow come up with an easier way, functional, analytic way to express this radiance. Okay, and you're on the unit sphere, right? The angle is on a unit sphere. So they said, well, let's expand the radiance in terms of spherical harmonics. Spherical harmonics are functions that lie on the unit sphere. You can characterize any function by, it's like a Fourier expansion, but it's on a unit sphere. And in general, those spherical harmonics are dependent on both the polar angle and the azimuthal angle. Okay? Those can be very involved and very complicated. So we said, okay, let's make our first assumption. Let's assume we have azimuthal symmetry, no dependence on phi. Spherical harmonics then simplified to Legendre polynomials. Okay? What that allows you to do, it simplifies the analytics, but you lose cases where, say, you have oblique incidence. If you have oblique incidence, then your radiance depends on phi. Okay? So we confine ourselves to normal incidence, and let's then expand L in terms of a Legendre polynomial expansion. So here I've written a Legendre polynomial expansion of the radiance, but cut it off at the first order term. The first Legendre polynomial is just a constant, which means that we're representing the angular variation of the light field just by a sphere. Okay, and we have 2D cross-section here. So basically it's saying, well, the light emanating from this location R has no dependence on theta. Okay? The first Legendre polynomial essentially gives us a cosine variation. Okay? So you have a dot product. This is J, we'll talk about what J, we call it the flux in our field. But it's essentially a dot product between this scalar, this function flux with the direction. This gives us a cosine variation. Okay? So it allows you to get an additional boost to this isotropic term in the forward scattering direction. So basically, cosine gives you a positive contribution for angles between 90 degrees, let's call this 90 degrees, and negative 90 degrees. Gives you a negative for 90 degrees up to 270. Okay? So this allows you to get a bias. You also use the same functional expression for your single scattering phase function, right? We've got to express a way of how light is redistributed upon scattering. And again, here we have the first term, which is a constant, 1, which is just uniform isotropic scattering, plus something that's a dot product, right? Your scattered direction and your instant direction, scattered direction. This is a probability distribution function, so it has to be, when you integrate it over all 4 pi steradians, you have to get unity, and that's why you get it free here. The G is essentially the single scattering anisotropy coefficient. It's the average of the cosine and scattering angle. So, and so when you represent that, the cosine, so let's take a preferred direction, call this theta equals 0. If you add on the cosine, this is what you get, right? You get, so this outer circle here on the left is our original green circle. You add on a cosine for between minus 90 and 90 degrees, and the cosine gives you a negative contribution here. And that's what gives you this bias, this directional transport line. And allows you to imagine that you have propagation, preferential propagation of light from regions of high fluence rate to low fluence rate. Okay? Now, if you just look at this, remember you have a zeroth order term and a first order term. And usually the first order term should be smaller than your zeroth order term. You know, that's the nature of usually functional expansion. If you look at this equation, you see right away that you start to get problems if your g becomes too high, right? For g values greater than a third, you're going to get some angles where the phase function actually takes on negative values. That's kind of nonsensical. There are actually angles where there's negative probability for scattering. Okay? And what are the g values that we typically use for tissue? 0.8, 0.9. So you can see that that's not working too well for us. That this radiative transport equation can't deal with light fields very well, which are highly directional. And you certainly get highly directional light fields because of the highly scattering phase function. And of course, if you start out with a highly directed source, you're actually starting with, highly oriented, forward-oriented propagation. Okay. Nevertheless, you can substitute these two equations into the radiative transport equation. You can then conserve energy, and you get actually two coupled equations because you have two terms. So you substitute this first order expansion in. You first collect all the terms that are of first order. You collect the terms that are of second order, and you get two equations. You have this fluence, phi, which we're familiar with. In the neutron transport literature, unfortunately for us, they call it the flux, so that can be quite confusing. J, we call it the flux. Neutron transport, they call it the current. So just to be aware of that in case you venture beyond biomedical optics, you might see that. So it's either fluence and flux or flux and current. But nevertheless, we actually reduce this integra differential equation into a coupled set of two partial differential equations, which are actually solvable. And since we're taking integral over all 4 pi solid angle here, and then you actually take the first moment, you have expressions for the zeroth order and the first order expressions of your source. So you integrate the source over all 4 pi steradians. You take the first moment here. And k here is just an operator. Again, it kind of just groups the time varying derivative term in UTR. If you then substitute this expression for j back into the first, you get your diffusion and or P1 approximation. So you get an equation which is second order both in space and second order in time. Okay? And it looks kind of like a diffusion equation for those of you who are familiar with diffusion equation. There are a couple differences. One is that a diffusion equation typically has a Laplacian in, say, temperature, if you're thinking of heat transfer. You usually have a first order time derivative term, and you have a source term. The two terms that you don't see in a classic diffusion equation is a term that multiplies the potential, temperature be it. And here we do have a term because we have to express our loss due to absorption. So there's something that's constantly removing light. There's nothing that absorbs heat per se in heat transfer. The other thing is that you have wave-like propagation in this P1 approximation. In classic diffusion, you don't have wave propagation. So you have a maximum speed of propagation. And you saw a second derivative term in the context of electromagnetic transport in Janika's talk yesterday. If you remember, do you remember, and of course he had a second derivative of the electric field with time. Do you guys remember what the coefficient in his equation was for that second derivative in time term? 1 over c squared, right? So, and the reciprocal of that and the square root of that is the speed in the medium. So you see actually that, okay, let's take the reciprocal of this. This is v squared, where v is the speed of sound, speed of light, divided by refractive index. So it's the velocity of light in the tissue. but we have this 3 hanging out here. So if you look at the speed of the wave-like propagation, it's wrong. It's v over the square root of 3. So you've got something wrong, but at least you have some wave-like propagation, which is good. So it turns out that this whole equation, where you keep the wave-like propagation term, is called the P1 approximation, and you can show that this is valid whenever mu s is much, much greater than mu a. If you want to get rid of this term, you can get rid of it so long as not just mu s is much larger than mu a, but the reduced scattering coefficient, mu s prime, is much, much greater than mu a. Remember, mu s prime can never be greater than mu s. It can only be less than mu s. Okay? It's equal to mu s in the case of isotropic scattering. Okay? And typically, that's what we do. We get rid of this term, and we just deal with the first order derivative. This is problematic because it violates causality, actually. If you get rid of the second derivative term and you have an impulsive source, at time just greater than 0, it predicts a finite light field everywhere. Okay, so there's infinite propagation. So just showing kind of the deficiencies that arise when you make such a radical simplification in both your functional expression for both the fluence rate and the phase function. Okay, none of these deficiencies are present in Monte Carlo. I just want to emphasize that because Monte Carlo is rigorous radiative transport. The other thing I want to point out is something that Professor Spanier mentioned on Monday, is that you notice that we have mu t, which is both mu a and mu s combined in the radiative transport, and a phase function. By the time you put in these simplifications, mu a and mu s don't appear independently anymore. You have mu s prime only, and mu tr, which is actually the sum of mu a plus mu s prime. And so all pairs of mu s and g collapse into mu s prime, and this solution to this equation will give you no sensitivity to your phase function. Okay, you have this first order similarity. And that, again, arises through this first order expansion. Okay, any questions about this? Okay. So the reason why we come up just more from intuitive basis, the reason why you must have scattering dominant over absorption is that you need to have a situation where your light field doesn't change very much with angle. Okay? And that's not going to happen if you don't have scattering to randomize the directions of the photons. Okay? Okay. So I'm going to switch to the delta P1, but one thing I want to emphasize here is that that there's a natural spatial decay of this equation. Let's just forget about the right-hand side. The right-hand side is just time-varying terms, so these two terms disappear in the steady state situation, and this is a source term. So if you go back to kind of your ordinary differential equations, you usually come up with a homogeneous solution and a particular solution, right? Homogeneous solution you can get without any, it's an important solution, it represents the basic eigenvalues of your system, and then you also have particular solutions which are dependent on the nature of your source. So let's get rid of the source term, and just two kind of cases that are very important is, number one, having a point source, isotropic point source in a spherical geometry. Professor Spanier showed you solutions in this case yesterday, on Monday. And then also a collimated source, planar decay of this system. And these are kind of your point spread function, either in space or in space and time, in these two geometries. Essentially, if you integrate this equation over all time, you get the spatial case. The reason that I mentioned this, I just want to point out that the spatial decay predicted by diffusion goes by this, this coefficient which we call mu effective, which is the square root of 3 times the absorption coefficient and the transport coefficient, which is the sum of mu a plus mu s prime. Okay? And this is often when you go and read our literature and people want to say, okay, the light penetrates to this depth. Usually they're calculating the reciprocal of mu effective. And as we will see, that can be really wrong. in many, many cases. Okay, and we'll see that shortly. And then here I did actually show the time varying terms. There is kind of a natural optical diffusivity coefficient, which I've denoted by kappa. It's the velocity of light in the tissue divided by 3 UTR. Unfortunately, many people define the diffusivity, they call it D, and they just do 1 over 3 times this, but that's actually not a diffusivity. It doesn't have units of diffusivity. So just be aware of that. Okay. Many of you may be familiar with these equations. Okay, so now let me just show you how the situation can be improved markedly if we try to do something with the collimated term for directed light. Does anybody have any questions before I move on? Yes?
Yeah,
Adrian?
Just to clarify,
Yeah.
the 2 examples you show there,
Yeah.
those 2 equations just represent the solutions of the steady state of the equation on the previous slide?
Well, this is time dependent. It's just basically for a impulsive source here. In this case, an impulsive isotropic source. And this is just also the time and space point spread function in planar geometry.
But that's just if you were to solve the equation on the I guess, second order part of the derivative on the previous page.
That's right, with a delta function source, basically.
Yeah, okay. That's
Yeah.
where you get this.
Yeah. Okay. Okay. So, how can we improve this situation? Clearly, there's a challenge potentially to deal with highly forward scattering. So I just wrote up, again, the radiative transport equation here, but what I did is that I just, for clarity, I put in the phase function that we use in standard diffusion approximation, which is what's called the Eddington phase function. There's a famous astrophysicist, Arthur Eddington, who came up with basically the first order expansion of Legendre polynomials. And what we're doing here now is that we want to decompose the light field at any location into 2 terms. One is the diffuse term, which is essentially exactly what we had before, the scattered light, which is essentially an isotropic term plus a first order anisotropic term, and collimated light, light that still remains directional. Okay? And I'm going to denote the direction of collimated propagation by omega naught. Okay? So at everywhere in the medium, you're going to have the radiance can come from 2 contributions: scattered light, which is diffused, and light that happens to still remain collimated. Okay? So I'm going to call that LD and LC. Similarly, so if you have a collimated light field come in, I have to figure out a way, well, how is that collimated light going to contribute to diffuse light? Okay? So at every point that that collimated light interacts with the tissue, scatters with the tissue, I have to say, well, how much of that light is going to stay collimated? And how much of that light is going to become diffuse? And we do that by adopting a slightly different phase function, which I call the delta P1 phase function. We're going to say, well, a fraction of that light we're going to keep scattering directly forward. I'm going to call that fraction F. You get a factor of 2 here because you're actually only going collimated in one hemisphere, not both hemispheres. So you have to do 2 to get it 1 over 2 pi here. And the remaining fraction, the 1 minus F, we're going to just keep it as the same Eddington phase function here. Okay? But since I've taken some of the light and kept it collimated, the G value is going to be different, right? Because now we don't have to take care of we don't have to accommodate all of that forward scattered light in that cosine term. We've taken some of that forward scattered light away, and you'll get a modified G star, a G, which we call G star. G star will be always smaller than G, okay? And that was one of the problems. We found out that in the standard diffusion way of doing things, once you get beyond G of 0.33, you're in trouble, right? Okay, so this is interesting. Now we have 2 parameters in our phase function. We've got this G star and this F, which helps us, right? Because before we have only 1 parameter, how we adjust that phase function. And that's actually what led us to the collapse of mu s with G. You get only mu s star. Now that we have two, we actually will find that two adjustable parameters, we actually can retain some sensitivity to our single scattering anisotropy. So in the same way, what we do is that we put in the substitution for the separation of the total radiance into a diffuse radiance and a collimated radiance. We put this phase function into here. We'll get two equations, one for the collimated radiance and one for the diffuse radiance. I'm going to ignore the collimated radiance for the moment and just look at the diffuse radiance. And if you write down what happens with the diffuse radiance back when we substitute back into the radiative transport equation, you get the exact same radiative transport equation, but with slightly modified optical parameters. Mu t star and mu s star replace mu t and mu s, where mu s star is essentially mu s minus mu s times 1 minus f. So basically, you're just looking at all of the diffuse light because we've taken off a fraction. Okay? And that, for the Henry-Greenstein phase function, that ends up being f, ends up being the second moment of the phase function. Okay? And mu t star is just mu a plus mu s star. And like I said here, g star will end up always being smaller than g. I've shown a g1 here because it's the first moment of the phase function. So essentially what we've done is that we've created a reduced problem because we've peeled off some of the light from the collimated source. But since this radiative transport equation has the exact same form as the radiative transport equation before, we can write down the solution in the delta P1 just like we did for the SDA, but just replace mu t with mu t star and mu s with mu s star. And you can do that, and that's what I'll do here. Okay? So you go through the exact same steps, the formulation is the exact same way, but one thing that you'll notice that the solution to the homogeneous, the homogeneous problem is the same. You have the same characteristic decay. The square root of this coefficient is mu effective. You know, mu effective is the square root of 3 of mu tr. The source has to be characterized slightly different, and this again is the equation for the diffuse light field. Now, the key thing here is that mu s star is actually sensitive to the second moment of your phase function. Okay? And mu a plus mu tr contains in it mu s prime, which is only sensitive to your first moment of your phase function. So actually solutions to this will not be equivalent for varying g for fixed mu s prime. So you actually gain some sensitivity to g, and we've shown many years ago that actually you can, using solutions to the delta P1, you can actually extract g from measurements of reflectance. Okay. So any questions about this? And so I'm going to show later on, what the impact of this is, where it helps you, where it doesn't help you, etc. Okay, so these are the governing equations. We need boundary conditions. Okay, and so let's talk a little bit about boundary conditions again, probably going back to high school physics. So typically we're working in a situation where we have an air-tissue interface. And so let's imagine that I've blown up our spatial scale quite a bit, and this point is literally just a hairbreadth below the surface, okay? And we have this angular distribution in our radiance, right? We got light emanating from that point in all directions. If that is coming out at the surface, we have to apply our Fresnel relations, right? And when you have light going from a higher refractive index medium to a lower refractive index medium, you get a bending of that light away from the surface normal. The other thing is that as that angle becomes stronger and stronger, less actually gets transmitted, and there's more specular reflection, right, for increasing angles. And there turns out to be what's called a critical angle, where no light can actually escape. That basically everything gets totally internally reflected. So this relationship between the angle of the incident light and the transmitted light is given by Snell's law. the product between the refractive index and the angle of incidence is equal to the product of the transmitted refractive index and the angle of transmission. And that this angle of incidence, where nothing can escape, is given by the critical angle, which is essentially just the arc sine of the refractive index in the transmitted medium relative to the incident medium. It's about 45 degrees, okay? Which is actually fairly small if you think about it, you know, kind of in an angular sense. Half of your light that emanates from that, if you had an isotropic light field here, which you seldom do, but if you do, it's like half of your light doesn't even escape, okay? And that will have an important impact on our internal fluence rates. Okay, so if you want to understand how this, you know, you can solve Fresnel's, Maxwell's equations at a plane interface, and you can get this beautiful equation for the amount of light that's reflected at that boundary. This is for unpolarized light. Basically, I've added the Fresnel reflectance for parallel polarized light plus perpendicularly polarized light, and then taken the average. This is what these results look like graphically. I've packed a lot of information on this slide. Essentially, on the y-axis here, on the left y-axis, I've shown the reflection, the amount of light that's reflected back into the tissue, how much light that actually is transmitted, which is available for our reflectance measurements. Okay, and then on the right-hand y-axis, I've actually shown the angle of transmission relative to the angle of incidence. Okay, so we see that actually the amount of light that is reflected back into the tissue is actually very, very small. Here it's just what's given by the specular reflection at normal incidence. It's just a few percent. And it's actually fairly flat. It's not very much, but once you get around 35, it starts to really explode right close to the infrared. And then obviously at the critical angle, everything is internally reflected. And then the transmission similarly drops. It's pretty much flat. Most of it escapes, and then you get close to the critical angle, and then it crashes. Okay? And the relationship between the angle of incidence and the angle of transmission is fairly linear here. There's some curvature here, and then, of course, everything gets frustrated and just gets coupled into an evanescent wave. And you get total internal reflection. Okay? So one thing that's important to note is that Monte Carlo, so number one is that the amount of light that gets reflected and the amount that gets propagated in transmission is dependent on the angle. And it varies with the angle on an angle by angle basis. And Monte Carlo does this balance faithfully. Okay? There are two kind of classical ways you can deal with these boundary effects. The first is known as photon splitting. So say you have a photon interaction in the kind of the photon trajectory. It comes to this point and it scatters, and the direction of the scattering is in this direction. It meets this surface, and there are two ways that we can do this. We can have what's called a pseudo collision at this surface, and we say, well, we actually split the photon. We say, hey, we know that we're going to have only a portion of the light that gets transmitted and a portion of the light that gets internally reflected. In a weighted Monte Carlo simulation, what we can do is that we can just apply a weight to both the transmitted photon and the reflected photon. So we take the weight that it has here, we hit it either with the Fresnel reflectance and let this photon continue to propagate in the medium. And if we have, and for the transmitted light, we hit it by 1 minus that. And if we have a detector there, if that's a point of detection, we just tally there. Okay, so that's one way to do it. But sometimes it's really kind of messy to deal with photon splitting. So there's another way, which is fully equivalent statistically, but may have slightly different characteristics in terms of the variance of the tallies and in terms of the convergence. And that is to only choose one fate for the photon or the other. And the way we do this, we call it, I call it roulette here. It's probably not roulette in the strict sense. But essentially what we do is that we have a pseudo collision here, and we say, hey, I'm going to choose either, we're going to allow the photon either to transmit completely or reflect completely. And we're going to do that based on a random number that we generate. We'll generate a random number between 0 and 1. If that value of the random number is between 0 and the Fresnel reflectance, we're going to allow it to reflect. If it's greater than that, we're going to let it transmit. Okay? And so that gives you, it converges to the same mean value, but the variance characteristics convergence make the difference. Yes, James?
Is the roulette case only used in the analog Monte Carlo, or is it also used in the weighting scheme as well?
Yeah, it can be used in weighting as well as in analog. Absolutely. Yeah. Jerry, do you have any additional comments to that? You can use that.
You can send a fraction through and a fraction back. So you can do it a third way, at least with the two. That's the two.
Say that you can send a fraction through and
Yeah, you can decide how much is transmitted and how much is comes back in.
that's on the left side here.
Those sorry.
We did that photon splitting, right? So photon splitting, we send a certain fraction internally
So
reflected.
you're using a weight there. Yeah. So
That's
how
right.
does your question relate to
I was just curious. It seemed like these related to Monday's talk that there's an analog and a weighting scheme, like in a separate. And I wasn't sure if you could use the seemingly analog roulette case on a general weighting scheme throughout.
Yes.
And the answer is
Yeah, I believe so. Yeah. Yeah, Jerry, the question was, can you actually use roulette? Roulette seems to be an all or nothing proposition.
Yeah.
And so Joseph's question, if I understand it correctly, is that he's saying, since this is kind of like an analog sort of way of dealing with reflectance, can you actually apply this to a weighted Monte Carlo simulation? And I believe the answer is correct. Yes, you can.
You can.
Yeah.
You can.
Yeah. Yeah. Jerry, do you want to comment at all about what might be the strengths or weaknesses of using photon splitting versus this roulette situation with respect to the variance or convergence?
There's an obvious weakness to splitting, which is that you get more fragments, you have more particles to follow, and that's a multiplier for your execution time.
Right, so photon splitting tends to increase your computational cost. Okay. Roulette, positives or negatives there?
Well, I mean, it's hard to say. Comparing the variances associated with those is difficult to say.
Uh-huh.
So it's doubtful that you get enough gain in variance from roulette to overcome the extra execution time. Remember, it's like the square, so that's a lot. I don't think there have been real studies on the comparison of the efficiencies of those two methods. I don't know if
Okay. Good questions. Any other questions while we're paused? Okay, so Monte Carlo really is able to do this detailed balance, and the first of many take-home messages of this talk is that the analytics can't do that, unfortunately. So what we do is that we conserve light at this boundary in an integral sense. Okay, so what we do is that we say, well, we can't do this detailed mapping because actually we don't have a function that allows us easily to do this detailed balance. So we say, we do the following. We say, well, here I'm doing an integral of the light such that z dotted omega is greater than 0. So if z is pointing internally into the tissue, this is looking at the forward hemisphere into the tissue. So this is showing what is the total light that is propagating down into the tissue. Okay? Right? We integrate the radiance over that forward hemisphere. I'm saying that that light has to be equal to the light that is traveling up, right? So this is z dot omega is less than 0. So since z is pointing downwards and we're looking at the dot product negative, it's all the light that moves up towards that boundary that then doesn't escape, that gets reflected. these two have to equal each other, right? The amount of light coming down can only arise from light that happened to be going up and gets reflected back down at this location z equals 0 just inside the tissue. Okay? This is in a case where we're not considering a source. Okay? Okay? This is the diffuse light. Okay? So even if you had a collimated source, that would be in the collimated portion of the equation. And so again, you can expand the L's in Legendre polynomials, put that together, and you get this boundary condition, which is dependent both on the fluence and the first spatial derivative of the fluence. This is sometimes called a mixed condition or a Robin condition in partial differential equation particles. So you can solve this. Okay. So just a few things that one has to recognize is that this refractive index mismatch introduces discontinuities in the magnitude and angular distribution of the radiance. And I talked about that, I think, on Monday. One thing that's important is that when you're integrating a light field, the fluence, over a certain angle, a certain cone, that gets distributed over a larger angle when it transmits to a region of lower refractive index. And that actually only a certain partial angular interval of your radiance actually is able to escape, right? Beyond the critical angle, it gets stuck in. And actually, you can see now that the reflectance that you measure is only sensitive to this partial cone or partial, it's not a partial hemisphere of light that is able to escape. Okay? But in that sense, the reflectance is communicating what is a sampling of that, a weighted sample, a weighted integral of the radiance right below the surface, which Jerry emphasized yesterday. So all the kind of metrics of interest are essentially weighted integrals of that radiance. Okay. So I'm going to switch gears now away from the math a little and really now start to focus on using solutions to try to gain some understanding of light distributions within tissue and how they're affected by optical properties and source configurations. So before I shift gears, are there any questions? Yeah.
So the Robin boundary condition you mentioned, you said that was for an isotropic source in the tissue. That you didn't say zero sources, right?
No, it's not. Well, this is a general condition. It will be valid at the boundary. This is actually under any conditions. You will have a source term if you'll have something on this right-hand side. This becomes inhomogeneous in some particular cases where you have sources. It depends on how you formulate it. Yeah, but the key thing here, the key message here is that we can only do this boundary condition based on hemispherical integrals. Can't do a detailed balance. There are other ways you can do this boundary condition, which I don't think have really been adopted in this field. So here, if you remember, in this analytic expansion of this, we express this as a zeroth order term and a first order term in the Legendre polynomials. You can go to higher order terms. And some people actually do the balance on each order. So they say, okay, let's look at the zeroth order term and do this hemispherical integral only on the first order and do it on the second order term. And you get a series of conditions. Jerry, do you have a comment to make on that?
It may be worth pointing out that if you're doing a simulation, instead of trying to solve the delta P1 in this way, then the difference between these methods that he's just described and that is that you have a photon by photon treatment of the exit angles and the angles, rather than an integrated representation. And so until n goes to infinity of the Pn, you won't get the exact.
Right.
But it's a very useful method, this one, for getting fast approximate solutions.
But remember, so what you're doing as you increase the order of that Legendre quantum expansion is that you're able to consider light fields with more angular harmonic content. And then if you express the boundary conditions in terms of each order of that expansion, then you're actually starting to try to do that detailed balance on an angle by angle basis because you're expressing the higher order harmonic content in that boundary condition explicitly. I don't know if that helps.
Yeah, I don't know if it's appropriate to talk about it now,
Mhm.
but I read papers where they use extrapolated boundary conditions.
Yes.
And I didn't know if you were going to talk about that at all.
I'm not going to. So those are ways to approximate this boundary condition. So it's kind of an approximation on top of an approximation. But yeah, and so the extrapolation boundary condition length is given by is related to the coefficient of this flux term, and then it's basically a dipole or monopole or quadrupole approximation. But you can solve it just by solving this boundary condition, and that's something unfortunately I don't think enough people do. But it's not that difficult to do, and in certain cases it provides much better results. Okay. Okay, so I want to talk about optical penetration depth. It's something that's mentioned a lot in the field. And I think, from my own point of view, I think it's mentioned a little too casually in the field. And so maybe I will give you my own points of view on what penetration depth is and how you may want to take more care. So there a few different cases I want to look at. Number one, this kind of pencil beam, meaning a beam of very narrow diameter propagating in the tissue. It's very important, obviously, in a lot of diagnostic techniques, certainly imaging techniques such as OCT. You often use such sources. That will generate fluence rate that decays with depth. And there are two things, from my perspective, that one may be interested in. If you have an incident irradiance impinging on the tissue, you may be interested at what depth does that light field decay to some fraction of that incident light field. Of course, we like to think in terms of exponential, so you say, okay, how about what is the fluence of 1 over e of that incident light field? I'm going to call that penetration depth. And I'm actually going to, all the results I'm going to show you are going to be using normalized parameters, normalized optical properties, and normalized power. So I'm going to just assume that the power is 1, and so that you can actually use my charts, which you'll have available, you do have available on the website, to actually use these charts for any set of optical properties. Okay. If you calculate the normalized optical properties, which I'll introduce very soon. These penetration depths are also going to be normalized, and I'll tell you in a moment how to do that. So this is the first thing. If I need a certain minimum magnitude of fluence in order to activate a phototherapeutic drug, for instance, what is the depth can I expect to get enough conversion of that light into an active mode? The other thing is, okay, I really don't care about a critical intensity. I want to know where is most of the light going to be absorbed. Okay, so instead of looking at when the light field decays to a critical level locally, I want to see, well, where is roughly 2/3 of my light deposited? Okay, and so that's really it scales with the integral of this fluence rate, right? So I say, well, where is all but 1 over e of my light absorbed? I'm going to call that the dose depth. So I choose the Greek letter for d, dose, delta. Okay, so penetration depth pi, dose depth delta. Okay? And so I want to understand how these two depths are sensitive to the nature of my source, whether I use a broad planar beam versus a Gaussian beam. How is it affected by optical properties? Okay. How is it affected by refractive index? And so hopefully, and you're going to fool around with this in your lab this afternoon, but I'll show you some results. So let's go ahead. So these are results from Monte Carlo simulations, and then I'm going to show you some results from standard diffusion and delta P1. So this is just a planar case. You have a huge beam, one-dimensional decay into tissue, no refractive index mismatch. Okay, this is a normalized fluence rate, so the incident fluence rate is 1, and the depth is expressed in terms of transport mean free path. Okay, so, and then I've looked at various sets of optical properties, ratios of the reduced scattering coefficient to absorption of 100, which is fairly typical, say, in the red or near infrared, to more highly absorbing cases, you know, reduced scattering or absorption of 10. So these are cases that we would expect standard diffusion to do fairly well. And the more absorbing cases where you know, reduced scattering or absorption is 3 or 1. Here we tend to anticipate there being problems. But such, you know, ratio of scattering to reduced scattering to absorption of around 3 is actually quite common in the visible, okay, around 500 nanometers. So if you're doing visible spectroscopy and you're probing the visible bands of blood, you can actually be in this case. So the first thing we see is that we have a slight, the maximum in this fluence rate actually doesn't occur at the surface. It occurs slightly below the surface. Does anybody know why that might be the case? Yeah?
In a very scattering media, I think of it as like a recycling of photons, basically. That there starts to be accumulation before much absorption happens.
That's one way. I think that's one way to think of it. It's very valid. The other thing is, maybe another way to think of it is that you're losing some light right at the boundary, right? There's some reflectance, some escape. Whereas here, it's very unlikely that a photon can scatter directly from this location and get out. It's going to get rescattered, recirculation, okay? But you also notice that that peak gets less prominent as the absorption goes higher, okay? Clearly, your penetration depth is much larger when the higher scattering that you get. So this maximum fluence rate occurs below this tissue surface, more prominent for high scattering. Now, if you put on a refractive index mismatch, how do you think these curves are going to change? If I change, so here we are index matched, okay? So it's like you're submerging the tissue in water, roughly. If you do have a tissue error interface, how do you imagine these curves will change?
Go down one.
Should go down? How many say down? Show of hands. How many say up? Very poor voting. Voting. It's a problem in this country. Nobody goes out and votes. Right? A lot of abstentions. You want to vote absentee? Right?
I guess I'm thinking that overall it might go down. They're just going to be losing. Oh, so is it?
Right now we're index matched.
Yeah, but is it normalized to fluence?
The incident.
The incidence. Not,
Yeah.
Okay. So then I would expect, I guess, them all to go down. Except maybe to have that peak be a little more prominent.
Why would it go down?
Overall, just because
Why?
either because of the index. Oh, is what kind of beam is it? Column?
Plain, huge beam. Okay, I'm normalizing it to the light that enters the medium, not so once you get in.
Oh, okay.
So forget about specular. Forget
Yeah,
about
yeah,
specular.
exact, so
Okay, and it's normal anyway. So even in 1.4, you're only losing a couple percent, and a
Right,
few
right.
percent.
So
So
I guess not really go down, and I would expect the light that would normally be escaping to maybe have internally reflected and kind of
boost, right? So what's happening is that you don't really get much since it's normally incident. Even you take care of specular reflection, you just lose a little bit through the specular reflection. But the light that tries to escape can't get out as easily anymore. And so what happens is that you pretty much get a significant boost in your light field inside. Now, of course, that boost is more prominent for a highly scattering medium, right? Because if you don't have much scattering, there's not much that gets back to the surface. It gets absorbed, terminated. And so as you increase your absorption relative to scattering, the difference, the impact of refractive index goes down.
So that must be fairly isotropic then, right?
What's isotropic?
I mean, you're saying that, I guess when I was thinking about it, I'm just thinking of specular reflection for the mismatch. But I guess the point you make is once it scatters, it can scatter back to the surface because
It's multiple light scattering. We have multiple light scattering, right?
So that's a case where, you know, it's not very forward scattering. I guess if it was very forward scattering, you would expect that effect to be less than that.
No, it's not true, because if you have high scattering, okay, you're in the diffuse regime, you're going to have multiple scattering, right? In a highly forward, even in a forward scattering situation, the light isn't being absorbed very much, right? So it can undergo hundreds of scattering events, thousands. And even if you have a G of 0.9, you're going to have significant backscatter. If you didn't, you would never have any reflectance, right? The only way you get reflectance is light that comes back to the surface, right? So you have roughly the same amount of, you have a certain amount of light that gets back to the surface, but since it can't, only about 45 degrees of that cone can actually get out, between 45 and 90, it gets internally reflected. So you actually trap a lot more light in the tissue. Another way of thinking about it, let's think of it from the detection side. If I had a tissue and I irradiated with a beam in air, and I measure the reflectance, I take the same tissue, submerge it in water, and measure the reflectance, in which case will I get more reflectance?
You expect all the diffusion.
Okay. Now, I put on standard diffusion approximation. And so here you see we do fairly well once you're in depth by about 2 to 3 L star. At the surface, you have some problems because the light field, especially in where you have refractive index mismatch, you have a very strongly anisotropic light field. One thing that you see here is that the decay is fairly good. Even at 10, you start to see some problems with the decay, meaning that the mu effective decay given by standard diffusion isn't quite good enough. And certainly once you get down to ratios of mu s prime over mu a of 3 and 1, you're in deep trouble. Okay. If you account for the collimated light through delta P1, you do much better. And in fact, you do much better even for cases where scattering is much more strong, where absorption is much more comparable to scattering. It's because you still take into account the direct collimated light. And in fact, one can show that even in the limit of pure absorption, delta P1 will recover Beer's law. Whereas in the case of diffusion, Beer's law is not recovered because mu effective in the case of mu s going to 0 doesn't give you the right decay in depth. Okay. Any questions? I'm seeing sleepy, glazed over eyes. Have I lost a lot of you guys? Are you guys okay? Okay, pretty straightforward. Okay, fine. Good. So delta P1 really improves things quite a bit relative to standard diffusion. So now I want to show these penetration and dose depths. Okay, so this is kind of a busy plot, but it has a lot of information, and it's a chart you can use actually in your lab. So what I've done here is I've plotted ratios of reduced scattering to absorption. Okay, all the way from basically purely absorbing to very highly scattering. And I'm plotting optical depths here, and it's normalized relative to mu effective. So if you have a dose depth of 1, it means that your penetration depth is 1 over mu effective, which is kind of the classic result you see in all the literature. And that turns out to be actually quite, and these are Monte Carlo simulations for the 2 different refractive index mismatches. And that is actually absolutely correct for the dose depth, for how much you absorb. And it's good pretty much for mu s prime or mu of 100. If you're interested in the penetration depth, what is the depth at which the light drops, the fluence rate drops to roughly 1 over E of the incident light dose, then it's some multiple of mu effective. And that multiple of mu effective gets enhanced when you have a refractive index mismatch because you're trapping light and you have deeper, you have higher light fields all the way within the tissue. Okay. So now the other thing that's interesting here, so this is very, very highly scattering. This is very highly absorbing, and you see everything converge to a number, it looks like around a little greater than 1.7. Can anybody off the top of their head explain? Well, actually, I have the answer down here. Don't see. So mu effective is the square root of 3 times mu A times mu TR. Mu TR is mu A plus mu S prime. Okay? Purely absorbing situation, mu S prime is 0. So you have the square root of 3 times mu A squared. Take the square root of that, you get square root of 3. And if you normalize to mu effective, that's basically square root of 3. Okay. So the first thing you see here is that this 1 over mu effective, if you're looking at kind of penetration of light to a fluence rate of roughly 1 over E of your incident, you're going multiples of mu effective. But that actually decays slightly, between, very highly scattering 100 to, 10,000. It decays quite a bit, actually. There's a big variation, a sizable variation, even between these optical properties. Now, the question is, how would standard diffusion do in predicting these? And this is what both standard diffusion, this is what standard diffusion does. So for this penetration depth, standard diffusion does pretty well. Starts to break down at around ratios of reduced scattering to absorption of about 50. Starts to, for this penetration depth. Penetration depth, it actually does fairly well, actually down to maybe mu S prime or mu F3. If you're interested in dose depth, it actually does not such a great job. Actually, I was quite surprised. Actually, it starts to break down even at these very high scattering ratios of around 100. You start to see this deviation. And of course, it completely is nonsensical, really horrible in the case where you have strong absorption. Okay. If you separate the collimated contribution from the diffuse contribution, actually you do incredibly well. And that's why I am an advocate of delta P1. Okay. Because it actually does a very good job across the whole band as far as these scalar metrics. If you look at the details of the light field, there are definitely problems in this intermediate regime, and I'll show you those in just a second. So it's not a panacea for everything. Okay. So now let's look at finite beams, right? I think Joseph asked, what are the sizes of the beams that they use in phototherapy? And so remember, they're very interested in making sure they can hit targets at depth. And what happens is that as you use smaller and smaller beams, the depth penetration is compromised because you have lateral dispersion of light. And so you're getting light leaking out laterally. Here I'm just going to show delta P1. This is for a highly scattering case. I'm normalizing the radius of the beam R0 to the transport mean free path. So here this is a case that I just wrote because it approximates the 1D case where your beam is the beam radius of 100 transport mean free paths. So like, what is that? 100 millimeters, 1/10 of a meter. It's a pretty huge beam. And how the radiance, the fluence rate really drops off as you narrow that beam. Delta P1 does very good at depth. You start to see breakdown close to the surface. Okay. So the scattering gives you a lot of lateral dispersion. You really compromise your penetration depth. Now, if you go to more highly absorbing cases, there's not as much scattering. And so here's the case for reduced scattering equal to absorption. And you don't see such a huge spread. You see, you have this huge spread here because scattering is just peeling out those photons to the side. If you have absorption, much more absorption, not much scattering, this spread is not as broad. You also start to see that even the delta P1, which is much, much better than standard diffusion, starts to really break down here. It doesn't do a very good job. Okay. So scattering is less available to do lateral dispersion in light field, which is actually good in some cases because a lot of the light treatments for the skin are done in the visible because they want to target high absorption by blood. So you can use narrower beams reliably and still not compromise your depth of penetration. But if you're in the therapeutic window, diagnostic window, then, if you use narrower beams, you may not get that photochemical activation as deeply as you would want. So you have to think about it. And you look at photodynamic therapy, usually they use, literally beams this large because they want to maximize the penetration of that light. And so here I'm just showing these penetration depths. Here you've got the slides. Here this is the penetration depth for the 1D case, the planar case, and then you start to see the compromise of how scattering compromises that penetration depth. This is for the high refractive index mismatch case, and so it's significant. If you're in a highly scattered situation, you're compromising by easily a factor of 2. If you even have, say, a 10 millimeter beam, which we imagine is quite large, your penetration depth is going to be compromised by easily a factor of 2. Okay. And there are dose steps here. Here are some just graphical visualizations of lateral dispersion. You're going to fool around and generate maps like this in your lab this afternoon. And so just to summarize, standard diffusion and delta P1 approximations are quite useful. They use analytic representations for the radiance and the phase functions. So we assume fairly simple analytic expressions. One is just a first order Legendre polynomial expansion, isotropic plus cosine theta term. In delta P1, we add a delta function to deal with these highly collimated sources. And it actually does a very nice job, not only in dealing with the collimation, but also in cases where you have high absorption. Because in high absorption, the light field maintains collimation because there's not much scattering. Monte Carlo transport solvers handle refractive index mismatch rigorously on a photon by photon or angle by angle basis using Fresnel relations. These analytic solvers don't do as good of a job. They really enforce energy conservation globally over using hemispheric integrals. Increases in the refractive index mismatch enhance total internal reflection and increase the fluence rates and the penetration within the tissue. That's very important. They also reduce the reflectance. The standard diffusion approximation gives you poor predictions in the internal fluence rates and optical depths. Depends on which metric you're looking at. Anywhere from, I would say, μs prime or μf. I would say probably 10 is a fair more generous